Hello, hi. In this video we're going to look at a first-person camera, but before we do that I wanted to kind of deconstruct a few concepts. To start with, coordinate system. So just as a reminder, you may be familiar with a polar coordinate system. Where we have a circle and any point on the circle, has a radius of 1 and an angle of theta, and we construct a right angle triangle here, and then we have that the point here is cos and sine, because the adjacent side is down here on the bottom and the opposite side is on the side there. Okay, so that's 2 dimensions. However, we want to look at 3 dimensions, and I want to say, how can we use angles to describe any position in 3 dimensions? Okay, so we've got our 3-dimensional system there. To start with, I would just construct a right-angled triangle in 2 dimensions. So we'll say, okay, here we have an angle theta. We have that. Okay, and then I say, okay, well, let's construct a hypotenuse here. Now, I think, if I remember this correctly, the convention is to actually measure the other angle away from the z-axis. It makes no difference, as you'll see. So let's measure this from the z-axis. We'll call this phi. Then this side here is, we have cos phi and sine phi, and then this is supposed to be mapping directly down. So then this radius here will be sine phi. Okay, so then, because the radius here is sine phi, not 1, then it's sine phi times cos theta, sine phi times sine theta. And so, to make the long story short, we get x, y, z is represented by, so x is sine phi cos theta, sine phi sine theta, and cos phi. Something like that would work perfectly fine. And just to make sure this makes sense, in this case, theta is our angle around the z-axis, how we're looking horizontally. Phi is our angle vertically, looking up and down. Phi equals 0 corresponds to looking directly up. Phi equals 90 corresponds to looking directly horizontal. Phi is 180 is looking directly down. Something like that. We'll work with that. The next concept I want to look at is, well, this is a little awkward here. What if I do this? Yeah, that works. Okay. I'm trying the best I can. Okay, so we're looking at walking. So when we're walking, we have the keys W, A, S, D. And a really simple way of doing this is to just test, is W on, and then, walk to the left. No, walk forwards. Geez, this is not good. Okay, so a simple test is just to test if a key is on and perform the walking. A more complicated test is we could have combinations of W, A, S, and D. So for example, what? S is backwards. If we go W and S at the same time, we want that to cancel out. Okay, so what we can do is, let's say, instead of a simple Boolean, we have a integer, which is an 8-bit number. So we have 0, 1, 2, 3. I'm just splitting it up like that. And let's say that, I don't know, W is 1. And I'm just going to focus on these lower 4 bits of the integer. And A is that one. S is that one. And D is that one. Because these bits are independent of each other, we can add these together, and the number that we get from adding these integers together uniquely represents the combination of buttons which is pressed. So just going back to our binary, this is 2 to the 0, so 1 times 2 to the 0 is 1, 2, 4, 8. So, for instance, let's go 1, 2, 3, 4. And so on. I'll continue this here. So if I see 1, the only way we can get that is to press W. If I see 2, the only way we can get that is to press A. If I see 3, the only way to press that is to, press A and W together. And so on. You can see how this works. So that's another concept that I'll be using. It's not a big deal because in the worst case, we'll be making 4 Boolean variables, but the C++ compiler reserves a full 8 bits for every Boolean variable, even though you're only using one of them. So this is a more compact way to work with it, and it also avoids this pointless like if else sort of thing to manually track all the combinations. Anyway, so those are the concepts. Let's get into the actual programming. Okay, hi. So let's get into the practical side of this. So for one thing, we are going to need to change our shader, because now instead of just a model, which tells us the position of the cube, and projection, which tells us how to view the cube, we also want something called a view. So we'll just pass this in, uniform matrix for view. Now, the importance of the view is, before we had, y as the upwards or downwards angle, coordinate, and z as forwards and backwards. But now I want to set it up so that it's, regular, like we would expect it to be. So the camera, what am I saying? So now z is upwards. And x and y are the horizontal positions. In order to do this, we need a view transformation, and what that does is it shifts the world so that the camera is the center of the world. It spins things opposite to the camera, it moves things opposite to the camera, and there it is. So where we insert this is, first we apply the model transformation, and then on top of that we apply the view transformation. And there we have it. That's our full standard transformation stack. Now we don't need to do much or anything. To the texture coordinates, they don't need to be transformed. Okay, great. Now let's go down, and this is all fine. To the main. Okay, so what we need to do here is we need to declare a player. Well, we're not doing the object-oriented stuff yet. That will come later. So for now, let's just declare some variables for the position and direction. So we'll go vec3 player position, and we'll just create the player at the origin. Okay, that's great. Now, what we want is we want another Okay, so we want to declare the direction. Now what we can do is we can declare a set of angles where each of them is the angle around its respective axis. So for instance, this first bit will be the angle around the x-axis. In our standardized, so we start with this sort of standardized coordinate system and then we transform it according to the player. In our standardized coordinate system, we'll say that x is forwards. So an angle around the x-axis would be kind of twisting around. An angle around the y-axis would be looking up and down. And remember from the previous section, I said 90 degrees should be looking dead horizontal. We'll see how that turns out. And then this angle here around the z-axis is our horizontal rotation. We'll just set that to 0 right now. Now, the name for this sort of system is called Eulers or Euler angles. Okay, cool. So we've got that. Then we'll go and set up everything. And we want something else. This is a first-person camera, so we want the mouse to control the movement. In other words, we want to hide the mouse, so we go glfw set input mode. We have for our window the thing that we're talking about. So we pass in a constant here. This is glfw cursor, and then the value that we're setting it to is glfw cursor hidden. And if we're playing a game and we click back to a menu, it's no problem at all just to call this again, and that will show the cursor again. This should all be tabbed over. Yep. Okay, cool. Just bunch this together a little more intuitively. Right, so then we declare our cube. That is perfectly fine. Our cube and all this stuff, our texture, our frame buffer. This is perfectly fine. Now, when we process the input, we also want to be able to change the player's position, etc. So let's go back to this process input function and we'll modify that. Okay, so we're going to take in that. We're also going to take in okay. So, if you're, you know what? I think I'll change this. It might be a little easier to see it all on screen. Okay. So, if you're watching this and you're saying, hey, Andrew, this is an error, this is a problem to do this. Yes, we'll get to that in a second, but I'm just going to do it, right? Okay, so what do we have? To start with, we want to track our state of our keys. So what I'm doing here, because this code executes every frame, we need to probably pay a little bit more attention to how it runs. So if I write something like this, then what this does is it creates a value and then copies the value into the variable. If we write this, then it directly inserts the value into the variable without that intermediate copy step. This does not make a big difference at all, but it's fine. It doesn't make a big difference at all, but in theory it should. Okay, so I should probably stick to convention, right? Who cares? Live on the wild side. Okay, so remember, the rotation around the z-axis is our horizontal direction. What we'll do is we'll read what direction the player is facing in, and then the direction they walk will be that direction plus a little bit. Like if we walk left, then we add 90 degrees to that, and that's the direction that the player moves in. Okay. Then we also want to track, is the player walking? Okay. So, now what we're going to do is we're going to get the state. So what we do, we call on our window, and we are looking for GLFW. Key W. We're saying, are we pressing that? So then this is just like I was describing before. We are going to increment this with different values depending on what we pressed. WASD. Okay, so now we've got that, we're going to interpret the result. So we've got an integer. Benefit of this is we can use a switch statement. Okay, so let's have a look at this. So if we get 1, then we're pressing W. But there's another case where we also should be walking forwards. That's when we're pressing W, A, and D at the same time. The A and D will cancel each other out, and the W is left. So the way we do that is we say, okay, W is 1, A is 2, so that's 3, D is 8, so that adds up to 11. So what I'm saying basically is we want to jump into this case if we get a 1 or an 11. Remember the way a switch works is the case that we get is the point that we jump in at, and then execution continues until the end, right? So that's why we need a break statement here, because for instance, if I write, what do we have? Case 2. Okay, right. So if we jumped in, because we're pressing W, then we execute this code, and then we're in, right? So we just keep going. It's like a railway track. Once we've switched in, we keep going. So then if we didn't have this break statement here, we would then continue and start walking left, which is why we always need a break statement. Just so this makes sense, I mean, you might say, hey, but we jumped in at case 1. Wouldn't we then evaluate and see whether case 2 is correct? And no, and the reason for that is the operation which allows us to chain multiple entry points to the same code, right? Because we jumped in at case 1, we then don't reevaluate case 11. We just jump in both cases. Does this make sense? Anyway, so let's continue here. So I'm going to speed this up a little bit. If you want, this is how I actually designed this code, is I wrote it all out on paper, all of the combinations, and then I manually went through and saw like which things cancel out. So if you want to follow along, that's how I would do it. Okay, back. So actually, what was I saying? Let's just, going to be a little lazy. I don't want to just sit here and type stuff. I mean, yeah. Just paste that in. Okay, there we have it. So this is working out all the combinations of buttons and appropriately setting the direction that we want to walk in. If nothing was pressed, then WASD will be 0 and walking will not be set to true. Okay, so now let's walk. Okay, cool. So if we are walking, then we step forward based on the direction that we want to walk in polar coordinates, so cos and sine, at a speed of 0.1. That's fine, that's acceptable. Now, if you're following along at home, you might find that your system kind of does this at a different frame rate. You might find that your system does this at a different frame rate. So in a future video, we'll be looking at frame rate independent movement. For now, we'll just kind of deal with it. Sorry. Okay, so now let's do the mouse stuff. So get the position of the cursor. Again, arguments here are our window, and then we need a pointer to a double for the X and the Y. These will be populated with the position of the mouse. So we pass in the variables we declared above and pass in pointers to them. And these will be populated. Okay, so we get the position, then we want to every frame reset the mouse to the center of the screen because we're going to track how far it moved away from the center. So set cursor position, again, window, then the X position and Y position. I'm going to cheat a little bit because we know what? We know that our width is 640, that's hard-coded, so we'll just go 320. 320.0 is a double representation. Half of 480 is 240. Just give me 1 second. That's better. Okay. So now we want to track, right? So we've measured the mouse position, we've reset the mouse. We want to track how far the mouse moved. So I'll make variable. So we've got that, and then the X position will be used to set the angle of the player. So we'll go around the Z axis. Actually, I'm gonna give the full debugging version. Okay, so we're gonna do that. We're going to increment our direction. Okay. Let's just do this. Mouse Y. Okay, that looks good. Okay, so let's go. So again, the rotation around the y-axis will be the vertical rotation. So difference is we have a maximum and minimum. So our maximum is 180 degrees, that's straight down. So we have that amount, and if that amount gets larger than 180, then we just want to pick 180, that's looking straight down. And then we have a minimum, which is 0 degrees, looking straight up. So we take that result, and if that result is less than 0, then we'll just set it to 0. This is a pretty standard pattern in programming, just min-maxing. No, sorry, min-maxing is something different in optimization. It's not the same. It's what we're doing. We're clamping is what it's called. Okay, that looks good. That looks good. So let's leave that. And remember, there's still that error that I haven't fixed, but there's still a lot of errors, but we're going to go through the process by hand as if we were programming this from scratch. Okay, so let's go to the events. So now we need to pass in player position, player Eulers. Okay, so that's fine, but then we need to update the view matrix. So the way this works is we have, let's call this GLM transform. So we have this function called lookAt. What does it take? Well, it takes a vector which represents the I position. Another vector, so the I position is where you're looking from. Then we have a vector for the center, which is where we're looking at. And then we have another vector which indicates the upwards direction. Now that is used in order to orient the view, because if I'm looking over here, then depending on where my up direction is, the view would be rotated around, if that makes sense. So what we need to do is, let's work these things out. Okay, so where are we looking from? We're looking from the player position. Now, where are we looking at? Well, we're looking from our position to our position plus a little bit. Now, we'll get this little bit by looking a radius of 1 away from the camera's eye. This is called a forwards vector. So we'll go so again, so we have sine of the vertical times cos of the horizontal, and then for the, so this is just the same as the bit I was talking about before. For the y, it's sine of the horizontal, and then finally for the z, it's just cos. Okay, so it's our position plus the forwards. Then we need to find our up direction. So we could just pass the vector 0, 0, 1, and that would be up. However, as the player looks around, that up vector rotates with the player, and we could actually hard code that rotation. But instead of that, let's do this. Let's say we'll have some vector which I'm going to call the global up direction. Then, based on the global up direction, we'll get our right direction. Now, I talked about this in a previous video on my channel, but here I'll demonstrate it with hands, right? So we have the global up direction, but the player's actually looking over here. Now, we can use the vector cross product to find a vector which is orthogonal to both of them. So we go this forwards vector cross with the up vector, and this is reversed, I think, on your view, but it's the right vector. So we'll say take the cross product of one vector and another one. So we have forwards cross with our global up. That's the right vector. So now what do we really have? Well, local to the camera, we've got its forward direction plus its right direction. And then if we take the cross product of that, that will give us its up direction, adjusted for the player's rotation. So we'll say okay, so finally we have and I think that should be fine. I think. Okay, so let's run this and see what we get. Not great. Let's investigate. So I think to start with, I'm going to try that again. Yeah, so see this, as we press or move the camera or anything, what am I thinking? I'm not even uploading the matrix. Okay. So what do we have? Just grab the same line as before. Okay, so look in there, get the view, and upload the view transform. Okay. Now let's try that. Again, still not great. So you've probably been cringing the whole time because you can see what the problem is. The problem is we are passing in the position and Eulers and everything just by value. So we take that thing in and we adjust it, and then we just discard it when the function ends. So two ways to get around this is we could pass in a pointer, but then we would have to use the address of operator down below. The easier way is when the AND symbol is used here, it is passing by value. So it gets a, it's pretty much the same. It's pretty much the same as a pointer, except that the syntax is a little bit cleaner. Okay, so you typically find when you're working with other libraries is a lot of C libraries will use pointers because they don't have this pass by value thing. And then a lot of C++ libraries will just use pass by value. Okay, so we've got it. What are we doing? We're looking up, we're looking down. That seems to work. Right. So now I just want to slightly adjust things. This is all fine. So down below, when we create the transform, now what? -3z is like down below us, so we want it to actually be 3 units in front of us. And I'm actually going to take out this rotation stuff for now. It's a little bit disorientating. Okay, where are we? Oh. This is very, very... sensitive. Just retry that. There we are. There we are. So I can go forwards, I can go backwards, left, right. I can do combinations. That's fine. There's a problem though. The problem is if I move my mouse to the left, the camera moves right. If I move a mouse to the right, the camera moves left. And this is what I was doing just before, where I wrote plus equals and then I changed it with a little smirk on my face because I knew that it was going to cause, it was not going to work. So just, and this is my point, you just experiment with stuff. That's all there is. Okay. Oh, there we are. Okay, so we move to the left, we move to the right. We can go do whatever we want. There is just one thing though. So, okay, I'm inside the cube. I look down, keep looking down. The view flips, right? There's this point where it kind of flips. I look up. That's not good. Okay, so what this is when we hit directly down, it kind of flips the view around. So what I like to do is I like to just go 1 degree before the breakpoint. So just 1 degree before direct down. There we are. Okay, directly down, that's good. Directly up, that's good. Now it's not right. It's not completely down or up, but like who cares? Okay. Awesome. So that was fun. We've got a first-person camera working. Hope you had fun. And yeah, see you in the next one. Bye.